If you've ever played with magnets, you've probably noticed that you can use them to pick up metal materials, but not other materials like rubber, wood, styrofoam, or paper. This is because certain metals, primarily iron, nickel, and cobalt, have magnetic properties. But it's important to remember that not all metals are magnetic. For example, here on the right, most of the coins are actually made of copper, so along with this piece of copper wire, the magnet actually cannot pick them up, while it can easily pick up the paper clips and screws which contain high amounts of iron. Every magnet has two poles, a north pole and a south pole. When you bring two magnets close together, the opposite poles will attract or pull each other together. Here you can see a north and south pole pulling each other together. If you bring two similar poles, meaning two north or two south poles together, they will push each other apart. Here you can see one magnet pushing another magnet away without actually touching it, as two north poles are brought close together. If you flip the magnet around, the south pole will attract the north pole. You can do the same thing, starting out with two south poles, which you can see here will repel each other just like the two north poles did. You can push the magnet without touching it, and then if you flip it around, the north pole will attract the south pole. Magnets can push or pull on each other because every magnet is surrounded by an invisible magnetic field. We represent the magnetic field with magnetic field lines that you can see here. Remember that every magnet has a north pole and a south pole. The magnetic field lines point from the north pole to the south pole, and the magnetic field is strongest where these lines are bunched closely together. Even though a magnetic field is invisible and you can't see it, it can still create a force on other magnetic objects, and you can detect it using a compass. A compass is a small bar magnet that is mounted on a pivot and is free to rotate. When there are no other magnets nearby, a compass will always align in the same direction. This is because the Earth actually has its own magnetic field. So, since the compass is a magnet, it will align with the Earth's magnetic field when there are no other magnets nearby to disturb it. However, if you bring another magnet nearby, its magnetic field can override the Earth's magnetic field and affect the direction that the compass points. Now, watch what happens when I bring the compass close to a magnet. You'll notice that the white part of the compass needle is always attracted to the magnet's south pole, and the red part of the compass needle is always attracted to the magnet's north pole. Remember that this is because the compass itself is a magnet with north and south poles, and that opposite poles attract. The compass always aligns with the direction of the nearby magnetic field. You can see that in this image where each compass is aligned in a different direction depending on its location. This is because the magnetic field lines curve around the magnet as you saw in the previous image, and each compass lines up with the magnetic field lines at its particular location. Another way to see the magnetic field is to use iron filings. Here you can see that if I cover a magnet with a sheet of paper and then sprinkle on tiny bits of iron filings, they will gradually take the shape of the magnetic field. This becomes more and more apparent as I sprinkle on more of the iron filings and shake the paper slightly to let them line up and take the shape of the magnetic field line. In this video, there's some white space around the magnet because the magnetic field is so strong that it pulls the iron filings in all the way to the magnet. Here's another example image that shows the complete magnetic field around the magnet using iron filings. There is also a relationship between electricity and magnetism. Here you see a battery which stores electrical energy next to a compass. You can see that when I move the compass around, its alignment doesn't change, indicating that it's just aligned with the Earth's magnetic field. However, watch what happens if I connect a wire to the battery's terminals. This causes electrical current, or the movement of electrical charge, to flow from one terminal to the other. Now, when I move the compass near the wire, its direction changes. This is because moving electrical charge generates a magnetic field. A magnet that gets its magnetism from flowing electrical current is called an electromagnet. You can make an electromagnet much stronger by wrapping a large coil of wire around a magnetic material like iron. Here you can see that if the electromagnet is not connected to a source of electricity, it doesn't generate a magnetic field and has no effect on the compass. Now, watch what happens when I connect the electromagnet's coil to the battery. This causes electrical current to start flowing through the wire, and you can see that it immediately changes the alignment of the compass. Now, as I move the compass around the electromagnet, its orientation continuously changes just like it did when I moved it around a bar magnet before. The magnetic field shape around this type of electromagnet is actually very similar to the magnetic field of a bar magnet. Electromagnets are very convenient because, unlike permanent magnets, you can easily turn them on and off. Here you see that when the electromagnet is not hooked up to the battery, it does not lift the paper clips. When I connect it to the battery and electrical current is flowing, this creates a magnetic field that attracts the paper clips. However, the moment I disconnect it from the battery, the magnetic field goes away and the paper clips are dropped. I can repeat this process as many times as I'd like. There is much more to explore in the world of magnetism. Magnets and electromagnets are used around you in everyday devices like motors, doorbells, and speakers all the time.